So far, whatever we have done in machine learning has assumed that data is labeled in a training set with some classes, positive, negative, buyer, browser, or type of animal, for example. But in the real world, there's nobody always telling you what classes there are. I mean, in some cases, you can measure it by figuring out which users actually bought something and which users didn't. But for example, in the case of sentiment, it's difficult to imagine how one would get that input, whether a sentence is positive or negative, without some human actually doing the labeling. So the question does arise, how do classes emerge from the data without any external human input? Or in the real world, how do we figure out that an animal is an animal, a table is an object, a chair is a chair, etc., without someone explicitly telling us what are objects and what are not objects? Well, the answer is clustering. In clustering, what happens is groups of similar users or user queries are clumped together or clustered together based on the terms that they contain. So if a large number of queries contained red flowers, yellow flowers, cheap flowers, etc., then all of these queries would get clumped into a cluster which talked essentially about flowers and their color. Right? Similarly, comments, which often use the words like, great, love, excellent, would go together and naturally form a cluster which talked about positive sentiment, whereas others which had words like hate, uncomfortable, very difficult, and stuff like that would get into another cluster which would hopefully be those which are negative. Now, those are the ideal situations. In practice, the clusters that emerge directly from the data need not be so nicely categorized into the classes that we actually expect. In the real world, for example, we might be looking at observations of animals having features like legs, the size of the head, and things like that, and we might group them based on which animals appear to be similar in terms of their head size or the number of legs they have or the noises that they make. And perhaps we'll get clusters which sort of look like the groups which represent the animal classes that we would naturally give. And that's probably how we actually assign classes to objects in the real world in the first place. An important part of all of these figuring out what classes there are from the data is the fact that we assume that the features on the basis of which classes emerge are given. This is very important to note because often clustering is highly dependent on which features one chooses. Later on this week, we will see how we might be able to find the features themselves from the data itself. But for the moment, let's assume that features are given. So the goal of clustering is to find regions of our space X. Remember our space X with features being the elements of x1 to xn. We want to find regions that are more populated than random data. Now let's look at this statement a little bit carefully. Regions means that things which are in the same region are close together or similar to each other just because their values of features, that is the x values, are close in some respects. So some agree, some don't agree, and even if they don't agree, in some respects they are close. For example, large and extra large are closer than perhaps to each other than perhaps to small. Secondly, these regions are not just regions which have a few instances in them, but are more populated than one would otherwise expect if the data were totally random, in the sense that if the x values for each of the features were chosen at random from all possible values that they could have. So what we're trying to see is, are there regions where the ratio of the probability of x falling in that particular region, given the data that we have, is larger than the probability that the data would take that value if data was generated uniformly. That means if it was completely random data, every element of x being chosen at random. Another way of looking at this is, let's suppose we have all our data, which is the black dots in the space here, and we set y equal to 1. So in clustering we didn't have an output variable since we didn't have the class, but we want to find these classes. So let's set y equal to 1 for all the dots which are actually there in our data. That means the actual observations that we experience in the real world are all set to 1. And then let's sort of imagine that we added to this data lots of other data which we chose at random. We just chose x values at random and just threw them into the data set, and those were the light blue or colored or the lighter colored dots, and we threw a lot of them in and we assigned them values y equal to 0. Now we want to find out, with this definition of our data, now it's no longer just the old data, but it's the old data plus this random data, how we could figure out what the clusters are. If we now define our f of x just like before, the expected value of y given x, where y is 1 for the data that we actually observe and 0 for the data that we added at random, then the expected value of y given x is just, essentially it'll be probability of x divided by probability of x plus the probability of the random variable being chosen. And if you just work this out, it'll be the ratio r over 1 plus r, because essentially you can divide the numerator and denominator by p0 and you'll get r over 1 plus r. Now this particular function will have extreme values. We'll have some areas where it's very large because a lot of the dots in that space have a 1 associated with them, and other areas it might not be large. There are no black dots in that area, but there are a lot of random dots. So to find regions where this function is large gives us clusters. Now this is quite important when we have big data, because in big data we can actually afford to do this kind of clustering, which is sometimes possibly even efficient. But that's not normally done because big data is quite new. So traditional means of clustering are k-means clustering, agglomerative or hierarchical clustering, and even our locality-sensitive hashing that we discussed in week 1 is a form of clustering, because it, in an unsupervised manner, groups similar items together. Of course, it doesn't care if the clusters are big or small, so often it doesn't give us great clusters, but it can definitely be used as a first step towards more careful clustering, where we're trying to find areas which actually have large values of f, that is, contained large number of points from our data, all of which are close together. Once you have a cluster, one can assign a class label to each cluster and say, okay, cluster 1 is class A, cluster 2 is class B. We can't really give them names because we don't really know how to name them. Well, as human beings, we figure out how to name them through language and collective agreement, but the computer doesn't know how to do that. So clustering is one way of classes emerging from data in an unsupervised manner. And we've seen one means of clustering, locality-sensitive hashing, even if it's not giving a great set of clusters. So we won't really study the other means in this course. There are other courses where you can get into all kinds of clustering algorithms as well as supervised classification algorithms. But we're going to move on to look at other kinds of learning. So the message here is clustering allows us to get classes from data without having to do any explicit labeling. But an important aspect is that one needs to have the features, because otherwise you don't have any basis on which to cluster. And if you choose your features wrong, then you'll get wrong clusters. Another nice point I'd like you to note is that we use the same formulation of f of x equal to the expected value of y given x with an appropriate definition of our space as including not only our original data points but also some random data, so we could use the same mechanism of defining the problem in terms of the function f of x. While this doesn't normally yield any practical benefit, it certainly allows us to understand both classification and clustering and some of the other techniques that we will study very soon with the same formalism. It also allows us to imagine a situation where if one were able to find decision boundaries of functions like f of x, or find regions where f of x is large or small efficiently, one could solve classification, clustering, and a whole bunch of other machine learning techniques with one set of methods. However, this remains a research area, even though much work has been done on this direction in the past, and assumes especially more importance now with big data, where querying the data directly often yields much better results than if one actually had very small amounts of data.